Hello everyone, welcome to the Module 4 of the RWTH project MOOC dedicated to multi-energy networks. This first part provides an introduction and tools for multi-lab experiments. In this presentation, we will cover the following topics: background and motivations, the fundamentals of multi-lab experiments with a focus on geographically distributed real-time simulation, followed by a description of some of the tools to perform multi-lab experiments. Finally, we present an introduction to one of these tools, particularly VilasNode, and conclude the presentation. So let's start with the motivation part. We are interested in transitioning to a smarter power grid, including cleaner energies, a high level of automation and communications, and distributed generation. In this table, we are going to show the main features of smart grids compared to conventional power grids. Regarding their structure, we have in conventional power grids a hierarchical structure mostly defined by TSOs and DSOs. While smart grids, the structure is networked with new players like microgrids, energy communities, and multi-energy systems. Regarding the flow of power, in conventional power grids, it's mostly unidirectional from generation to consumers, while in smart grids, it's multidirectional enabled by prosumers. The type of generation is mostly centralized in conventional power grids, and it's mostly bulk generation. On the other hand, in smart grids, we have a generation which is highly based on distributed energy resources interfaced through power electronic converters. This means that regarding the inertia, we have a high inertia in conventional power grids and a low inertia in smart grids, which also means that the type of control systems in conventional power grids is rather simplified, while in smart grids we have more advanced and pervasive control systems, leading to the concept of cyber-physical systems, so where these complex algorithms are implemented and represent the cyber part, which interacts with the power system, which is the physical system. This means that in the case of conventional power grids, we have a low interaction with ICT infrastructure, and in the case of advanced control system, we need a higher interaction with ICT infrastructure and an increased amount of Internet of Things devices. This means that the uncertainty is low in the case of the conventional power grid, because mainly the sources, the energy sources and the demand are predictable, and in the case of smart grids, it's high uncertainty due to the increased amounts of renewable energies, electric vehicles, and energy storage systems. So this final row of the table concludes in regards to the testing difficulty, that in the case of conventional power grids is going to be low, and the testing of new applications can be easily done in one single laboratory. But in the case of smart grids, because of all these new elements that we have highlighted, it means that the complexity is much more difficult in a single laboratory. Existing approaches for smart grids include the following approaches. While offline simulation is normally applied in the early stages of the development process, real-time simulation allows to have hardware-in-the-loop setups. In this way, we can connect and test control or power devices to the simulator. This setup extends the capabilities of the laboratory so that the devices can be rigorously tested and then deployed in the field. However, when it comes to interfacing power devices, The low voltage signals coming from the real-time simulator have to be amplified. This step is known to introduce additional delays and potential instabilities. Pure hardware approaches are the most suitable for testing since the setup matches the one found in the field. However, it lacks of flexibility. Now, as pointed out in the previous slide, smart grid testing imposes several challenges, mainly due to the complexity of the scenarios, which often require intradisciplinary and interdisciplinary competences, such as in such a way that implementing a relevant scenario would require high investments and efforts in operation and organization. An interesting solution consists in integrating multiple research infrastructures. Given the multidisciplinary nature of smart grids, multiple research infrastructures have developed expertise on a particular topic. The idea consists in coupling the simulators and devices found in these laboratories so that more complex scenarios can be built. The main advantages of this approach are an improved collaboration and exchange of knowledge among the researchers, allows to pool hardware and software resources so that large-scale scenarios can be built with higher levels of detail. Additionally, the interaction between the academy and the industry is promoted. So in this figure, we can see in the left-hand side a single research infrastructure performing a simulation comprising several subsystems. In this case, because only one simulator is used, one real-time simulator, the same modeling approach and the same solver are used. In contrast, in a multi-infrastructure integration, we can achieve more complex scenarios by performing a distributed experiment. In this case, multiple simulators with their own modeling approach and their own solver exchange outputs over a communications channel. These multi-lab experiments are closely related to the concept of geographically distributed simulation. In the past and nowadays, several universities and research centers have demonstrated the feasibility of this integration, with research infrastructures integrating in Europe or even between Europe and the United States. For power systems, geographically distributed real-time simulation addresses the following topics. First, decoupling method, which can be based on the exchange of control signals, or in the case of multiple system exchanging power, then the coupling is made based on electrical signals. In this case, it can be asynchronous AC, synchronous AC, or DC. This coupling method would depend on the setup and the system dynamics. We need to define the proper interface algorithm and if the signals that are exchanged need to be subject of some transformation, such as the Park transformation. Finally, we need to define the communications protocol. We need to define the proper transmission rate based on the coupling approach. If there is required some orchestration module, we need to take care of the cybersecurity of these communications. And finally, because the communications channel introduces relevant time delays, then we need to implement proper time delay compensation algorithms. As the experiments grow in complexity, there are some desirable requirements, including interoperability, automation of experiments, and methods accounting for the impacts of communication networks. Interoperability considers data exchange and information models. In the former case, we want to have flexible communication interfaces supporting multiple communication protocols. In the case of information models, it is important to agree upon this standard like the Common Information Model. Additionally, In the RWTH2 project, we have developed tools for multi-lab experiment automation like research infrastructure as code and configuration management. These aspects are gonna be discussed in the next part of this MOOC series. Finally, we want to evaluate the impacts of the network communications in terms of packet loss and other variables, other indicators like latency and jitter. Now let's have a look at some of the existing communication interfaces for multi-lab experiments. The first one is the VLAS framework, which is a toolset that facilitates the setup of co-simulation scenarios. It's an open source project consisting of the VLAS Node Gateway, which is a high-performance communications gateway supporting protocols like IP-UDP, MQTT, Modbus, and IEC 61850. Faster dynamics are achieved through VLAS FPGA. Moreover, a soft real-time layer is built using the VLAS controller interface, which allows to forward simulation data to the VLAS web platform. VLAS Web allows online interaction and visualization of the multi-laboratory experiment. The second tool for laboratory coupling is Yonder, which works based on local databases, which are synchronized with a remote database through a replication mechanism. Yonder provides two levels of communication. At level 0, it implements bidirectional and secure communications. Samples are represented using a simplified scheme based on keys and values. At level 1, Yonder provides support for IEC 61850 communications, and more recently it was improved for supporting an interoperability REST API developed in the RWTH2 project. More about this will be discussed in the second part of this MOOC series. Finally, LabLink is a middleware for data exchange and synchronization. LabLink is based on the MQTT messaging technology. On top of it, LabLink provides high-level communications and mainly three communication modes: messaging, RPC, and data points. An interesting functionality of LabLink is that it implements a synchronization service which also takes care of the initialization of the multi-research infrastructure experiment. This tool has been demonstrated in experiments dealing with multi-energy networks incorporating hardware in the loop. Let's finalize this presentation with a short introduction to the VLAS Node tool. The scenario that we are going to implement is based on a simulation of the SIGRE medium voltage benchmark, which is shown on the right hand side. Apart from VLAS Node, there's a couple of additional tools. In this case, we are going to use our real-time simulator is going to be DPSim, which is an open source real-time simulator which also implements an interface to VLAS Node. We are going to implement communications between the real-time simulator and VLAS Node using MQTT. For this reason, we are going to use, in this case, the Mosquito message broker. If you want to reproduce this example, we have this easy to fulfill requirements. Basically, you need to install a working version of Docker Compose as well as a web browser. The resources of this demonstration are included in this repository, in the repository included in this QR code. This is a schematic representation of the experiment. So in the left hand side, we have the DPSim simulator, including an implementation of the SIGRE medium voltage benchmark. we are going to send the bus voltages and phases using the Villas Node interface, which is going to publish data on a specific MQTT topic, and in turn these samples are going to be read by Villas Node. In this case, Villas Node subscribes to the corresponding topic. The protocol conversion that we are going to show in this example is between these MQTT messages and a REST API. In this case, it's going to be the universal API developed in the RWTH2 project. Remember that more details are going to be provided in the next presentations of this MOOC series. For this example, our client is going to be just the command line tool curl, with which we are going to be able to read the samples that come from the simulator. The elements of this example setup are implemented as Docker containers, and they are included in this Docker Compose file, which is available in the repository of this MOOC part. The Docker Compose includes containers for Villas Node, the DPSim simulator, and the MQTT broker. In the case of Villas Node, we need to provide a configuration file with which we define the signal and the message mapping. This is the Villas configuration file. So here we have an element describing the different nodes comprising this setup. In this case, the nodes correspond to the ones shown in the schematic of the experiment. It's basically this MQTT node and the API node. The mapping between these nodes, the routing between these nodes, is made by the paths element, and here we are telling it to forward all the messages coming to the MQTT node to the API node. This additional element called hook, in the case of this specific hook type, will allow us to visualize the messages that are incoming to this path. Additionally, we need to define the specific signals with a name and a specific type. So in the case of the SIGRE medium voltage benchmark, we know that there's a total of 15 buses, and then we need to define a signal, a corresponding signal for the voltage and the phase of each bus. This has to be made also in the case of the output signals of the universal API. This is for the specific example. This is for this specific Villas example. In many other examples, we don't need to define the specific signals in this level of detail. But basically, what we can do is we just define the signals for the node 1 in magnitude and phase. We need to do some copy paste for every bus, and then with this we will have our implementation of Villas Node by means of this configuration file. We will deploy everything using the docker compose up command. And here we're going to be able to get the main the main tool with which we interact with the real-time simulator DPSim. In this case, this Docker image will set up a Jupyter environment for us, because one of the main advantages of a DPSim is that it comes with a Python interface so that we can develop easily new scenarios. We are interested specifically in the example located in this root. So we are going to go to the examples directory. There's going to be a villas directory, and we want to verify that we have this dpsim mqtt sigre and vprofiles.py file. Because it's a Python file, then I am going to run it from the command line. So what we are going to do is to execute the Python 3 command followed by the root to this specific file. So it's in the examples. We need to execute the terminal from the root folder of dpsim. So here we execute Python 3 examples villas followed by the name of the file that we want to execute, and this is going to execute the simulation for us. Now we can verify in the terminal, in the other terminal running the Docker Compose, that we are indeed receiving all the signals that we wanted. But more importantly is to verify through the universal API that we have access to these channels, and this is done specifically for this API definition through the endpoint I was showing right here. So this is going to list for us all the available channels provided by the universal API. Now we want to access a specific sample of this of a specific bus voltage. So for that we use the after the channel element here, we put the ID of this specific bus. In this case, let's say that we want to see the phase of bus number 2, and we add this sample element at the end. So it's very likely that the simulation is already finished. Then I will run it again to show you that we can indeed get the value of the phase of this bus every time. So as you can see, the timestamp changes every time we make the request, and also the phase value. So let's summarize the presentation with the conclusions. So we saw that the energy transition opens a multitude of new applications enabled by smart grids. The energy system is becoming, as a result, more complex and multidisciplinary. This complexity impacts the testing processes of smart grid applications, mainly testing processes based on real-time simulation. In this case, a single research infrastructure would require high amounts of investment and effort to build the knowledge and tools required for the desired simulation scenarios. Multi-laboratory setups extend the capabilities of a single research infrastructure by pooling hardware and software resources with partner research infrastructures. Moreover, this approach enables knowledge exchange and motivates the involvement of the industry. Additionally, Multi-lab integration implies some challenges, since simulator coupling requires the exchange of inputs and outputs over a communications network. For this, we need appropriate tools, and in this case we reviewed three of the tools for multi-lab experiments, namely Yonder, Villasnode, and LabLink. Finally, we presented an example of using Villasnode for converting data from the DPSIM simulator in MQTT format to REST API. This API is intended for interoperability, so that protocols not currently supported by Villas can be included as API clients.